Hi, welcome to Sam's Maths Lectures. This is my fourth lecture on group theory now. Okay, so we're going to start by talking about products and sums, so ways in which we can combine groups. So let G dot and H star be groups. Then we can define the direct product as we call it usually G cross H, direct product G cross H, and we'll sort of use the tensor product symbol for that, is the group. And so of ordered pairs, so we're just taking the Cartesian product of the two underlying sets, G, H, where G in G, H in H, under element-wise or component-wise multiplication. And so G, H with G dash H dash is going to be defined as G dot G dash H star H dash. Okay, so this is a group that sort of inherits its associativity from G and H being groups. It has identity of EG, EH, and then the inverse of this, so G, H inverse is just G inverse, H inverse, and in general we sort of have G, H to the power of n is G to the n, H to the n. Okay, so this generalizes to any number of groups, so let I be a set. Generally we'll sort of hope that I is finite, but if not countably finite, countably infinite at most. I guess you could do it for uncountably, but I haven't come across that before, such that for all I and I, Gi with dot I is a group. Then the direct product now is written as the product for I and I of the GIs, and the set here is the set of functions f from I to the union of all the GIs, the sort of disjoint union, I guess you could say, of GIs, such that for all I and I, f of I belongs to GI. Okay, so we can sort of think of f as mapping each position of the group to the element that takes up that position. So we could have that I as 1, 2, 3, and then f1 is just the first component, f2 is the second component, and so on. But this way is sort of easier to work out. And we have that f dot g defined by f dot g of I is just f of I, so component-wise again, the I product with G of I. Okay, so we still have component-wise multiplication, and the indexing set here is arbitrary. However, if I is infinite, we may restrict to the direct sum, and the direct sum is a subgroup of the direct product. So we write this as the direct sum of I and I of GI, and it's a subgroup of I in I of the direct product, and we define this as F in the direct product group such that the sort of number of I in I such that f of I is not the identity of that group is finite. Okay, so we have only finitely many non-trivial components here. And we can see that that's a subgroup because obviously if f has finitely many non-trivial and g has finitely many non-trivial, then g inverse is also finitely many non-trivial, and then the sum of the two finite numbers is also finite. Okay, so that's the direct sum. We won't worry about that now, but it comes up in graded rings when we talk about homology. Okay, so if we have two groups, G and H, then the order of the product group is just the product of their orders. Okay, so that's nice and simple. We also have that the order of the groups doesn't actually matter, so G cross H is isomorphic to H cross G under the isomorphism phi, G cross H to H cross G, which maps GH to HG. Okay, and this is called the transposition generally because we're swapping the elements. Transposition. Okay. Now we also have that, say the order of G in G is M and the order of H in H is N, then the order of GH, which we can just write like this, we don't need the extra pair of brackets, is the lowest common multiple of M and N. Okay, so clearly GH to the LCM MN, which we'll say is equal to KM, and that's also equal to LN for integers K and L, is equal to G to the M to the L to the K, G to the H, to the N to the L, but that's just E to the K, E to the L, which is just the identity. Okay, so that's good. The order then must divide this, so OGH divides the lowest common multiple, because otherwise we could use the Euclidean division algorithm to show that the order is not the order, there's a lower number. Okay. However, we also have that what am I doing? Yep, so GH to the LCM MN is equal to just the identity again. So, no. Okay, so the order G H here is equal to trivially E. It must be true. And so therefore G to the O GH equals E, so that means that O M divides the order, and repeating that H to the O GH is equal to E, so N divides the order, and so therefore the LCM of M and N divides the order of GH, and so we can sort of use these because O divides L and L divides O, then they must be equal. Okay, good. So if we then take the groups Z, M and Zn, where m and n are coprime. So the highest common factor of m and n is 1, which means that their lowest common multiple is just their multiple, equals m, n. Then we take the element 1, 1 in the group z to the m cross z to the n, has 0, 1, 1 is just the lowest common multiple of m and n is mn, and so because the order of this has mn as well, we must then have that zm cross zn is congruent to the cyclic group zmn. Okay. If the numbers aren't coprime, then things get a little bit different, but yeah, that's fine. Okay. If we go back to thinking about cosets now, recall that the left cosets are gh of some h subset of g. We have that gh and hg are the left and right cosets, and in general, gh is not equal to hg. Okay, so let's suppose that the cosets are equal. So suppose for all g in g, gh is equal to hg. So this is now a special type of subgroup. Okay, then h is normal. So a normal subgroup is a special kind of subgroup, and we give this special notation with a triangle instead of the less than or equal to sign. So h triangle g, h is a normal subgroup of g. Okay, and so what that means is that for all g in g and for all h in h, there exists a second element h dash in h such that g h is equal to h dash g, i.e. if we pre-multiply by g inverse, h is equal to g inverse h dash g, and we can do this the other way around. So for all g in g, for all h in h, we must have that g inverse h g is also in h. Okay, so that's an important part of the normal subgroup. Okay, now this is really useful. So when we have two subsets A, B, subset G, we call their product just AB, and that's just the set of all products A dot B, where A is in A and B is in B. And that normally doesn't mean anything, but if we take the product of two left cosets of a normal subgroup, so we'll call this N now, then Gn times G dash N, okay, this set we can flip the first set because of N being normal, so that's Ng G dash N, which is the set of all N dot G dash dot N dash, where N and N dash are in N, which we can then say is N dot G twiddle, which is equal to G dot G dash dot N dash, where N dash are in N, which is N G twiddle N, which is G twiddle N, and then obviously because any two elements of N are themselves an element of N, we have that this is G twiddle N. Okay, so what this means is that for any normal subgroup, the left cosets or the right cosets form a second group. Okay, so under this special operation, Gn times G dash N maps is equal to G dot G dash Okay, so this is a group with identity En, which is just n, and inverse is just G inverse n. Okay, and so we call this group the quotient group. G divided by n. Okay, so what we've done is we've effectively divided out n from our group. Okay, and so some things to note: if G is abelian, then obviously if G is abelian, then we already have for all H in some subset H of G, and for all G in G, then we have that G inverse H G is just H, which belongs to H. So any subgroup is normal. So we can divide out any subset we want. Okay. Now if we take the group Z plus and the group Z NZ plus, okay, so the n multiples of n, we have that this is in fact a subgroup because the multiples of 2 include 0 and includes inverses. Okay, and so because Z is is an abelian group, we must then have that NZ is a normal subgroup of Z. Okay, and so we can then take the cosets of that. So those are sort of 0 plus NZ, 1 plus NZ, ... and this goes up to n minus 1 plus NZ, as n plus NZ is just equal to 0 plus NZ. And so we can see quite quickly that Z divided by NZ is isomorphic to the integers modulo n. Okay, so that's sort of another way in which we can construct them. Okay. Then if G is finite, then clearly because there are the index of n in G, left cosets of n, so we must have that the modulo of the order of the quotient group is G is the index of the subgroup in G, and that is just the order of G divided by the order of n. Okay, so that's quite good as well. Then if we take some group G, the center of G is the set of all elements ZG, which is the set of all elements which commute with all other elements. So that's G in G, such that for all H in G, GH is equal to HG. Okay, so this is a subset. Now clearly E always belongs to Z of G because EG is GE by the identity sort of definition. So if we let F be in ZG, then for all H in G, we have that HF equals FH. So if we now pre and post multiply by F inverse, we find that F inverse H is HF inverse. So F inverse is in the center, and if G and F belong to the center, then clearly for all H in G, GFH is where we can pass the G across to the other side because G commutes with all elements of G. So we get FHG, but then so does F, so we can pass the F through as well. So we get F HGF, so GF is in ZG, which means that, of course, ZG, the center, is a subgroup. But also, we then have, for all Z in the center of G, and for every other element of G, then clearly H inverse Z, H, because Z competes with all elements, we then have that's equal to Z is belonging to the center. So in fact, the center is an ideal of G. Not an ideal, a normal subgroup of G. Okay. And then we can then take the quotient G over ZG, and so we quotient out all of the elements that commute with all other elements, and then we lose that property is centerless. Which doesn't mean it doesn't have a center, because the center is always a subgroup, so it's just the trivial subgroup and no other elements. Okay, if G has no normal subgroups, or no proper non-trivial subgroups, so no normal subgroups except G itself and the identity, which is trivially a subgroup, then G is simple, because we can't really factor it out into other parts, because obviously if we can factor away a subgroup. Okay, so G is simple, and there is a complete classification of finite simple groups and a complete banger called finite simple group of order 2, which I think concludes this lecture. So I'll come back next time to talk about the first isomorphism theorem. Thanks for listening.